There's a moment, just before an answer reveals itself, where expectation feels certain. Years of theory, equations, and observation align into a single belief about how the universe should behave. And then, a new observation arrives, and that certainty begins to shift. If we could look far enough, deep enough into the past of the universe, what would actually be there? For decades, science offered a clear expectation. The early universe should have been simple. Small, irregular structures slowly gathering matter, gradually building into the galaxies we see today. Complexity in this view is something that takes time. The James Webb Space Telescope was built to test this expectation, not to overturn it. Its purpose was precise: to observe the faintest, oldest light, and in doing so, provide direct evidence of how the first structures formed. But there is a difference between expecting an answer and confronting one. When Webb began observing the most distant regions of space, it was not simply extending our vision. It was accessing earlier moments in the universe's history. Light from those regions had travelled for billions of years, carrying with it information from a time when the universe was still young. What appeared in that data was not what the models had prepared us for. Galaxies, not in their early, chaotic stages, but already massive, already luminous. Systems containing billions of stars, showing signs of structure that suggest development rather than emergence. And most importantly, they appeared far too early. Within a few 100 million years after the beginning of the universe, these galaxies were already present. To place this in perspective, imagine compressing the entire 13.8 billion year history of the universe into a single year. In that scale, these galaxies would appear within the first few days, fully formed rather than gradually taking shape over time. This is where the question sharpens. It is no longer simply about what exists in the universe, but about when and how it came to exist. A useful teaching insight here is this: scientific models are not just descriptions, they are timelines. They define how long processes should take. When observations consistently violate those timelines, it suggests that the processes themselves are not fully understood. At this point, it is important to remain precise. The discovery does not overturn the foundations of cosmology. The Big Bang model, the age of the universe, and the general framework of structure formation remain well supported. What has changed is something more subtle and more important. The universe appears to have formed complex structures much faster than our models predict. So the central problem emerges naturally, not whether galaxies existed early, but how they formed so rapidly under conditions that should have limited their growth. To approach that question properly, we must begin with a fundamental principle, one that quietly governs every observation we make. We must understand light, not just as something we see, but as something that carries the past forward into the present. Because once that idea is clear, a natural question follows, one that appears again and again when people try to understand the universe. When we look out into space, are we seeing it as it is now, or as it once was? If that question is taken seriously, the answer requires a shift in how we interpret what we see. When we observe distant objects, we instinctively treat them as they exist now. This assumption works in everyday life, where distances are small and light reaches us almost instantly. But, at cosmic scales, this intuition begins to fail. Light, although extremely fast, does not travel infinitely fast. It moves at approximately 300,000 kilometers per second. Over short distances, this delay is negligible. Over astronomical distances, it becomes fundamental. A useful way to understand this is through simple examples. When we see the moon, we are seeing it as it was about 1.3 seconds ago. The sun appears as it was more than 8 minutes in the past. These delays are small but measurable. Now extend this reasoning. The nearest star beyond the sun, Proxima Centauri, is observed as it was over 4 years ago. More distant stars represent light that has been travelling for decades, centuries, or longer. At this point, the principle becomes clear. Observation is not just spatial, it is temporal. This leads to an important concept known as look-back time. The farther away an object is, the longer its light has taken to reach us, and therefore the further back in time we are observing it. A teaching insight here is worth emphasizing. Every telescope is, in effect, a historical instrument. It does not show the universe as it is, but as it was when the light began its journey. This transforms the act of observation into something more precise. We are not simply looking at distant objects, we are reconstructing a timeline. With this understanding, the role of the James Webb Space Telescope becomes more specific. It was designed to detect extremely faint light from extremely distant sources, light that has been travelling for billions of years. In practical terms, Webb allows us to observe the universe at a stage very close to its beginning. But there is an additional complication. As light travels across the expanding universe, it does not remain unchanged. Its properties shift in a way that gradually moves it beyond the range of human vision. So the next step in understanding Webb's observations is not just how light travels, but how it changes during that journey. And that leads us directly to the next idea: how the expansion of the universe alters the light we receive. If those galaxies appeared too early, then the question becomes more precise. Are we interpreting what Webb sees in the correct scale of the universe? Because at that scale, the universe does not behave in the way our everyday intuition suggests. It is not fixed, it is not still, it is expanding. Since its earliest moments, space itself has been stretching, not objects moving through space in the usual sense, but space expanding between objects. This distinction is subtle but essential. Now consider what this means for the light Webb detects. The light we receive from distant galaxies began its journey billions of years ago. But during that journey, the universe itself has been expanding. As space stretches, the light travelling through it stretches as well. Its wavelength increases. What begins as high-energy light gradually shifts toward lower energy. Short wavelengths extend into longer ones. Light that may have once been visible is transformed beyond the range of human vision. This effect is known as redshift. But here is the important point. Redshift is not just a change in appearance. It is a direct consequence of the universe's expansion. It encodes how much the universe has grown during the time that light has been travelling. In other words, when Webb observes distant galaxies, it is not just detecting old light, it is detecting light that has been altered by the growth of the universe itself. A useful teaching insight is this: the deeper we look, the more we are not just seeing earlier objects, we are seeing a different state of the universe governed by different conditions. As we push further back, this effect becomes extreme. The oldest light is stretched so significantly that it exists only in the infrared region. This creates a critical limitation. Any instrument that relies on visible light will simply miss these earliest signals, which is why Webb was designed differently. It was built to detect this stretched ancient light, to operate in a range where the earliest information about the universe still exists. And this is what allows Webb to reveal galaxies at such early stages, not because they were hidden, but because their light had shifted beyond the reach of previous instruments. Seen in the true scale of the universe, Webb is not just observing distant galaxies, it is observing a universe that was smaller, denser, and evolving rapidly, one where the rules of formation appear to have unfolded faster than expected. And to understand how Webb makes such observations possible, we must now examine how it was engineered to detect this deeply transformed light. To detect such deeply transformed light, observation alone is not enough. The instrument itself must be designed around the physics of that transformation. This is where the James Webb Space Telescope differs fundamentally from its predecessors. Traditional telescopes, including those that defined modern astronomy, were optimized for visible light. This made sense for studying nearby stars and galaxies, where light remains largely within the human visual range. But, as we have seen, the earliest light in the universe no longer exists in that range. It has been stretched, shifted into infrared wavelengths. So the design of Webb begins with a simple but demanding requirement. It must detect infrared light with extreme sensitivity. At the center of this design is its primary mirror, measuring 6.5 meters across. This large surface area allows Webb to collect extremely faint signals, photons that have traveled for over 13 billion years. Each photon carries limited energy, so capturing enough of them requires both size and precision. But collecting light is only part of the problem. Infrared radiation is closely associated with heat. Any warm object emits infrared signals, including the telescope itself. If not controlled, this would overwhelm the very signals Webb is designed to detect. To address this, Webb uses a multi-layered sunshield, roughly the size of a tennis court. This structure blocks heat from the Sun, Earth and Moon, allowing the telescope to cool to temperatures below -230 degrees Celsius. A useful teaching insight here is this. Webb is not just looking into cold space, it must become cold itself to function accurately. Its position also matters. Webb is placed at what is known as the second Lagrange point, approximately 1.5 million kilometers from Earth. At this location, gravitational forces and orbital motion create a stable environment where the telescope can maintain a constant orientation, with its sunshield always facing the Sun. This ensures a consistent thermal condition and a clear, unobstructed view of deep space. In this configuration, Webb operates in near-perfect darkness, shielded from interference, tuned specifically to detect infrared light. This combination of sensitivity, cooling and positioning allows it to observe photons that were previously beyond reach, signals that carry information from the earliest stages of the universe. And when those signals were finally captured and analyzed, they did not simply extend our view of the cosmos. They revealed something that did not fit within our existing expectations. Which brings us to the next step. What the early universe was actually expected to look like before these observations began to challenge it. Once we understand how Webb is able to detect this ancient, stretched light, the next step is to ask a more grounded question. What exactly were we expecting to see? This expectation did not emerge from speculation. It was built over decades, through a combination of theoretical physics, large-scale simulations, and observational evidence. According to the standard cosmological model, the early universe followed a sequence that is both logical and constrained by known physical laws. In its earliest state, shortly after the Big Bang, the universe was extremely hot, dense, and opaque. Light could not travel freely because matter and radiation were tightly coupled. After approximately 380,000 years, conditions changed. The universe cooled enough for atoms to form, allowing light to move freely for the first time. This moment left behind a measurable signal known as the cosmic microwave background. A useful teaching insight here is that this radiation is not theoretical. It has been directly observed and mapped in detail, providing a snapshot of the universe at that early stage. Following this, the universe entered a period often referred to as the cosmic dark ages. During this time, there were no stars, no galaxies, only diffuse matter and the gradual influence of gravity. Over time, small fluctuations in matter density began to grow. Gravity pulled matter together into increasingly dense regions. These regions formed the first structures, small, irregular, and faint. These early systems, often called proto-galaxies, were not well organized. They lacked defined shapes and contained relatively few stars. Their development was gradual. As time progressed, these smaller structures merged. Through repeated interactions and accumulation, they formed larger and more complex galaxies. This process is known as hierarchical formation. A simple way to understand this is to think in terms of accumulation rather than sudden creation. Large systems emerge from the combination of many smaller ones over extended periods. This model leads to a clear prediction. The early universe should have been dominated by simplicity, small, chaotic structures slowly evolving into larger, ordered systems over billions of years. This expectation is not arbitrary. It is supported by simulations that incorporate gravity, thermodynamics, and the behavior of matter on cosmic scales. So, when Webb began observing the early universe, there was a well-defined picture in place, but the observations did not align with that picture, which brings us to the central tension. What Webb actually saw did not match what the universe was expected to look like at that stage. And this is where expectation and observation finally separate in a way that cannot be ignored. If the early universe was meant to be simple, then what Webb revealed requires careful attention, not because it is dramatic, but because it is consistent. Across multiple observations, the same result appeared: galaxies. Not small, irregular formations in their earlier stages, but systems that already carried significant mass. In several cases, these galaxies contained billions of solar masses worth of stars. This alone would be noteworthy, but the issue is not just their size, it is their timing. These galaxies are being observed at a stage when the universe was less than 500 million years old. To place this in context, that represents a very small fraction of cosmic history. Yet within that limited time, these systems appear to have already undergone substantial development. Some observations go further. There are indications of internal structure, features that suggest organization rather than randomness. In certain cases, disk-like formations have been identified, raising the possibility that ordered systems were already emerging. A useful teaching insight here is this. Complexity in astrophysics is not just about size. It reflects processes, star formation, gravitational interaction, energy feedback, all operating over extended periods, which makes the central issue clear. These galaxies do not appear to be in the process of forming. They appear to have already formed. Independent research teams, using different datasets and analytical methods, have reported similar findings. The consistency of these results reduces the likelihood that this is an observational error or a statistical anomaly. Instead, a pattern begins to emerge. These galaxies are too massive, too bright, and too structurally developed for the time at which we observe them. This is not a single exception that can be adjusted within existing models. It is a repeated outcome that demands explanation. At this stage, the problem becomes more precise. It is not simply that galaxies exist early, but that they exhibit properties that should require far more time to develop. And once a pattern reaches this level of consistency, it changes the nature of the discussion. The question is no longer whether the observation is valid. The question is how such systems could have formed under conditions that, according to our current understanding, should not have allowed it. Which leads directly to the next challenge, not just the presence of these galaxies, but the time required to build them. If these galaxies appear fully formed, then the difficulty is no longer observational. It becomes quantitative. We must now ask a stricter question. How long does it actually take to build a galaxy of this scale? A galaxy is not a simple object. It is the result of continuous star formation, gas accumulation, gravitational interaction, and energy feedback. Each of these processes operates under physical limits. To form tens of billions of stars, large amounts of gas must collapse under gravity. That gas must cool, fragment, and convert into stars over time. Even under efficient conditions, this process is gradual. Now consider the timeline suggested by Webb's observations. These galaxies exist within a few hundred million years after the beginning of the universe. This is less than 5% of its current age. To achieve such growth within that window, star formation would need to occur at rates far beyond what we observe in the present universe, not just briefly, but continuously. A useful teaching insight here is this. Increasing the rate of a process is not always sufficient. Physical systems introduce feedback. As stars form, they release energy through radiation and stellar winds. This energy pushes against surrounding gas, slowing further star formation. In extreme cases, it can halt the process temporarily. So, there is a natural limit to how fast galaxies can grow. Simulations that incorporate these constraints consistently show that building galaxies of this size should require billions of years, not hundreds of millions. Yet the observations indicate otherwise. This creates a timing problem, not because galaxies exist, but because the duration available for their formation appears insufficient. We can think of this in simple terms. If a process normally takes hours, and we observe the result after minutes, then either the process occurred under very different conditions, or our understanding of the process is incomplete. In this case, both possibilities must be considered. Either the early universe allowed for much faster and more efficient star formation than current physics predicts, or there are additional mechanisms influencing how matter collapsed and organized. At this stage, the disagreement is not subtle. It is a direct conflict between theoretical timelines and observational evidence, and when such a conflict persists across multiple independent observations, it indicates that the issue is fundamental rather than accidental. Which leads us to the next layer of the problem. If galaxies formed this quickly, then other structures within them may have followed the same accelerated path. including the most extreme objects we know, black holes. If galaxies formed faster than expected, then we must extend that question further. What about the most extreme structures within them? Because galaxies are not just collections of stars. At their centers, they often host black holes, objects whose formation and growth follow their own set of constraints. And here, the problem deepens. Observations of the early universe indicate the presence of supermassive black holes. Not small ones, but objects containing hundreds of millions of times the mass of our Sun. And they exist at a time when the universe itself is less than 1 billion years old. To understand why this is difficult, we must consider how black holes are expected to grow. In standard models, black holes begin as smaller seeds, formed from the collapse of massive stars. From there, they grow by accreting matter, pulling in gas and surrounding material over time. But this growth is not unlimited. There is a theoretical limit, often referred to as the Eddington limit, which defines how quickly a black hole can accumulate mass before the energy it emits begins to push material away. A useful teaching insight here is this: growth in astrophysical systems is often self-regulating. The very process that allows growth also creates resistance to it. Even under ideal conditions, continuous growth at the maximum allowed rate would require hundreds of millions of years to reach the masses we observe. But real systems are not ideal. Accretion is not steady, it is interrupted. The supply of gas fluctuates. Energy output disrupts the surrounding environment. Growth occurs in phases, not as a smooth, uninterrupted process. Yet despite these limitations, the observations remain consistent. These black holes appear already massive, already developed, and already active in a very young universe. This extends the earlier problem rather than replacing it. It is not just that galaxies formed quickly, it is that multiple complex systems, stars, galaxies, and now black holes, seem to have evolved on compressed timescales. At this point, the issue becomes layered. Each independent line of evidence points toward the same conclusion. The early universe was more efficient at building structure than our current models predict. And when different phenomena point in the same direction, the significance increases. We are no longer dealing with isolated anomalies. We are observing a consistent pattern across different scales of structure, which leads to a broader implication. If both galaxies and the black holes within them formed earlier than expected, then the underlying framework that supports their formation must also have developed earlier. And that brings us to the largest scale of all, the structure of the universe itself. There is a recurring line of inquiry that surfaces whenever people try to understand the universe at its largest scale. How is everything arranged, and how did that structure come to exist so early? If galaxies and black holes both formed earlier than expected, then the question must expand once again. What larger structure allowed this to happen? Because galaxies are not isolated systems. They exist within a much larger framework, a network that defines how matter is distributed across the universe. This structure is known as the cosmic web. On the larger scales, matter in the universe is not spread evenly. It forms a vast network of filaments, clusters, and empty regions called voids. Galaxies are not randomly placed. They are located along these filaments, often concentrated where these structures intersect. A useful teaching insight here is this: the cosmic web acts as a scaffold. It provides the underlying structure upon which galaxies form and evolve. According to current models, this large-scale structure develops gradually. Small density fluctuations in the early universe grow over time under the influence of gravity. Dark matter plays a central role, forming halos that attract normal matter and guide the formation of galaxies. This process, like galaxy formation itself, is expected to take billions of years. But the observations from Webb introduce a complication. If massive galaxies existed very early, then the structures supporting them must also have existed. A galaxy of significant size requires a corresponding dark matter halo to hold it together, and that halo must be part of a larger network of structure. So, the implication is direct. If galaxies formed earlier than expected, then the cosmic web, at least in part, must have formed earlier as well. This extends the problem beyond individual objects. We are no longer examining isolated systems. We are examining the timeline of the universe's entire architecture. A simple way to understand this is through dependency. Galaxies depend on dark matter halos. Those halos depend on larger structures. If one appears early, the others must precede or accompany it, which means the entire sequence of structure formation may have unfolded faster than predicted. At this stage, the issue is no longer limited to star formation rates or black hole growth. It reaches into the foundation of cosmology itself. The models that describe how matter organizes on the larger scales may be incomplete or missing critical factors that influenced early development. And when a problem reaches this scale, it changes how we interpret everything that came before it. Because if the structure of the universe formed earlier than expected, then the processes within that structure were operating under conditions we do not yet fully understand. Which leads us to the final question. If the observations are consistent, and the models remain largely successful in other areas, then what exactly is missing from our understanding of the universe? There is a question that appears repeatedly whenever people try to make sense of discoveries like these. Does this mean our understanding of the universe is wrong? If the structure of the universe formed earlier than expected, then the conclusion must be approached with care, not haste. Because despite the tension we have explored, the foundations of modern cosmology remain strongly supported by evidence. The universe is still approximately 13.8 billion years old. The Big Bang remains the most consistent explanation for its origin. The large-scale behavior of matter and energy continues to align with established theory. What has changed is not the foundation, but the completeness of the model. The early universe, as revealed through these observations, appears to have been more active, more efficient, and more capable of forming structure than previously understood. A useful teaching insight here is this: scientific models are not final answers. They are working frameworks, refined continuously as new data becomes available. When observations extend beyond the limits of a model, it does not represent failure. It represents an opportunity to improve the model. In this case, the contradiction is clear. The timeline predicted by current theory does not fully match the timeline revealed by observation. But contradictions in science have a specific role. They identify the boundaries of our understanding. Throughout the history of physics, progress has often begun in this way. A result appears that cannot be easily explained. At first, it seems like an anomaly. With further confirmation, it becomes a pattern, and eventually it leads to a revision of the underlying framework. We are now at that intermediate stage. The observations from Webb have not overturned cosmology, but they have exposed a gap, something missing in our explanation of how the early universe evolved. This missing element may involve processes we have not yet fully modeled. It may involve conditions in the early universe that differ from current assumptions, or it may point toward new physics that has not yet been incorporated into existing theory. At this stage, the exact answer is not yet known, but the direction is clear. The universe has presented us with evidence that challenges our expectations, not in isolated cases, but across multiple independent observations. And when that happens, the appropriate response is not to dismiss the data, but to examine our understanding more carefully. Because every time the universe appears to contradict us, it is not creating confusion, it is providing information. And that information, when studied with precision and patience, is what allows our understanding to move forward. The question, then, is no longer whether something is missing. The question is what we have yet to discover.